Today we are going to see about solution to optimal power flow. So the optimal power flow is a very large and very difficult mathematical programming problem. Very large and very difficult, as we see in the last class, like how many constraints it is being involved. So how the difficulty also you know even with one constraint itself, for 3 unit system we are taking more than half an hour for solving a problem. Imagine 5 to 6 constraints and a problem. It is very difficult and also very large programming problem also. Almost every mathematical programming approach that can be applied to this problem, like a simple Newtonian's problem to maximum of Lagrange's and optimization techniques, like many solution techniques is being applied to this problem, and even though attempted, and it has taken developers many decades to develop the computer codes for this optimal power flow problem reliably. So here if you see, like, these are the solution methodologies for solving the optimal power flow problem. The first one is lambda iteration method, gradient method, Newton method, linear programming method, linear programming optimal power flow method, interior point method. So among this Newton's method is a normal solution methodology. It gives the solution fast, but it may if the inequality constraints are there, so it may gives the problem for the solution. Okay, so if you see the lambda iteration method, losses are represented by B matrix, B coefficient matrix, or penalty factors may be calculated outside by the power flow. Penalty factors may be calculated outside the power flow. This form the basis of standard online economic dispatch program. Standard online economic dispatch program. So next solution technology is gradient method. Gradient method are slow in convergence and are difficult to solve the problem in the presence of inequality constraints. So inequality constraints is very difficult to solve. Like equality constraints, it's very easy to solve. 3 or 4 equality constraints also. Sometimes while solving the problem, you can easily incorporate. You can frame one equation and you can try to solve the problem. You can get the solution. But inequality constraints, with one inequality constraints, we solve the problem in the class. So that itself somewhat complex. So imagine like 5 inequality constraints or 6 inequality constraints present in the problem, and we are going to solve the problem by a gradient method. Is very difficult task. This Newton method. So Newton methods was introduced by the great scientist Newton. So it's a very simple technique. Very simple technique. Like it will give accurate answer. It will give accurate answer, but it takes many time to solve the problem. It's a complex problem, but it gives accurate answer. Even though while solving inequality constraints, this OPF is is not at all easy. It may gives the problem while solving inequality constraints, and as well as even though it gives the fast convergence. Next solution technology is linear programming method. Linear programming method, I think already you studied in in your M3, linear programming method, non-linear programming method. So this is one of the fully developed method now commonly used. It can easily handle inequality constraints, non-linear objective function, and constraints handled by linearization. Non-linear objective function and constraints handled by linearization. So next technology is interior point method. Interior point method, this is also another technique that is fully developed and widely used methods of OPF. It easily handles inequality constraints. That is interior point algorithm. Interior point algorithm or interior point method. So here what we introduce is lambda iteration method. This method forms the basis of standard online dispatch codes as we solved like a lambda iteration method. This technique works well and can made to run very fast. Transmission system does not produce a dispatch of generation that will avoid overloads, voltage limit violation or security constraint violations. The objective of OPF is usually minimized. Always we are minimizing the losses and as well as minimizing the generation losses, startup generation losses. In some cases, as the power transfers, it might be maximized. Okay, in some cases it might be maximized. This minimization problem can be of maximization problem also. We shall designate this objective function as small f, the equation that guarantees the power flow constraints met with the designated as g of z is equal to 0. Okay, so we have taken the objective function as small f. This equation guarantees the power flow constraint that are met with the, so this g of z is a power flow constraints. Note that we shall only concern with the variable vector z. Okay, so we have framed the vector z. Okay, so inside the z vector, it comprises of all the variables. Okay, so simple form g of z is equal to 0, like that we have taken. So this vector contains adjustable controls, bus voltage magnitude, phase angles, and as well as fixed parameters of the system. Later we shall break the variables into set of state variables, control variables, and fixed variables. Okay, so in like while doing complex calculation, what they will do is, for simplification, they will say simply write as g of z is equal to 0, f of x is equal to 0, like that. But if you take what is f of x, that is objective function, it might be a very complex. And even if you take this g of z is equal to 0, this z combines all the like voltage magnitude, phase angles, fixed variables, control adjustable variables, everything combines together in a vector. So don't think like g of z is equal to 0. It's very easy like that. So it is very complex. Next, OPF can also solve for optimal solution with inequality constraints on dependent variables such as line MA flows. Okay, so line MA flows that is taken as here h minus less than or equal to h of z less than or equal to h plus. Okay, so that we have taken as MBA flows that we have taken as h. Okay, in addition, limits may be placed directly on the state variable or control variables. Okay, within this limits, that is z minus less than or equal to z less than or equal to z plus. That is called state variables or control variables. Okay, these are called state variables and control variables. So I think you already studied in power system analysis, state variables or control variables. The OPF problem then consists of minimizing or maximizing of an objective function subject to equality constraints or inequality constraints and the state control variable limits that we know. Either the objective may be minimizing or sometimes it might be maximizing objective subject to equality constraints and as well as inequality constraints, like what we have seen, like voltage constraints, then reactive power limits, then MVA limits, then voltage limits. Like that, many inequality constraints are there. Okay, so subject to equality and inequality constraints and as well as the state and control variables. Okay, so this development illustrative example is chapter is concentrated on OPF. This is widely linear programming OPF. This is widely used and only requires AC or DC power flow programs. Let's see the simple gradient method first of all, then we'll see the rest of the method. So this is the gradient method of solving OPF. So in this section, we consider only the objective function to be the total cost. Objective function to be the total cost of generation. Okay. So the objective function is taken as sigma up to all generations I is equal to 1 to n fi of Pa. That you know. This is the objective function. Where the sum exceeds all the generation on the power system, including the generator at the reference bus. So we shall start out defining the that is x equal to theta I, okay, into ei. Okay, so theta I is nothing but change in the phase angle, that you know. Okay, while sending we are sending the Gauss-Seidel method, Newton-Raphson method, we have seen. While sending, we send with the voltage, exact voltage, and as well as the change in the phase angle. Okay, so that also initially how it is varying or not, that we are going to see. So theta I also taken. So theta I also taken and ei also taken. This modulus form on each PQ bus. Okay, so theta I on each PV bus. So that we have taken as state vector x, and another one vector y is defined as, okay, so this is the reference bus parameters. First is that is theta k ek on the reference bus. Next, pk of net, qk of net on each pq bus. Okay, again pk of net and ek of sch for each qv bus. Here, so the vector that is x, this is the x vector. Okay, this is the x vector, this is the y vector. So in the y vector we have taken as reference bus and each PQ bus and as well as QV bus. Note that vector parameters that must be specified. Some of these parameters are adjustable. Okay, adjustable. For example, generator output, that is PK net, and the generator bus voltage. Some of the parameters are fixed. Some of the parameters are fixed as OPF calculation is concerned, such as P and Q at each load bus. To make this distinction, we shall divide the y vector up to two parts, that is u and p. Okay, so again if you take inside all the parameters, So it will become very more. So what we are doing is, for simplicity, we are just making the, for simplicity we are just making this y into two terms, that is u and p. Okay, again u and p, we are dividing this y parameter. Okay, where u represents the vector of control. So u represents the control or adjustable variables, and p represents the fixed and constant variables. Okay, u represents adjustable or control variables, p represents the fixed or constant variables. Note that we are also only representing equality constraints at this point. So we are not representing inequality constraints. For simplicity, we are neglecting the inequality constraints, and only we are representing equality constraints. Finally, we shall divide this set of m equations that govern the power flow as g of x comma y is equal to pi of e comma theta minus pi net. Okay, qi e comma theta minus qi net for each pq, that is load bus I. Then again pk of e comma theta minus pk of net for each PV generation bus k, not including the reference bus. So like that, we have taken the g of x comma y. Next, we must recognize that reference power bus is not an independent variable. That is, reference bus generation always changes to balance the power flow. We can't specify it at the beginning of the calculation. We wish to express the cost or objective function as function of control variables and as well as state variables. So what we are taking is, we are taking the objective function as a function of control and state variables. So that's why we are dividing the cost function as follows. That is, cost function is equal to sigma all generation fi of pi plus f reference of p reference. Okay, so all the generation and as well as reference cost also we are added. The first summation does not include the reference bus. The PI are all independent control variables, where P reference is a dependent variable. Fi of PI is a control variables that already we have seen. Then P reference is a dependent variable. We say that PI are in the vector u. Okay, PI are in the vector u, and the P reference is a function of the network voltage and the angles. That is, P reference is equal to P reference of E comma theta. Okay, so P reference is a function of like a network voltage and as well as the phase angles. So next, again this above cost function becomes like we need to substitute like P reference. So cost function becomes fi of P plus f reference of P reference into E of theta. Okay, into E of theta, E of theta, that is nothing but f of x comma u. So the which is Lagrange function. Now you know the object function. Now it's time to frame the Lagrange's function. You know what is Lagrange's function? Lagrange's function is defined as objective function plus some constant into constraints. So Lagrange's function of x comma u comma p is equal to f of x comma u, that is already we derived, no? F of x comma u plus lambda dash into g of x comma u comma p. This is the Lagrange's function, where x is a vector of state variables, u is the vector of control variables, then p is the vector of fixed parameters, then lambda is vector of Lagrange's multipliers. So lambda is nothing but constant, that is called Lagrange's multiplier. Next, G is nothing but set of equality constraints representing the power flow equation. G is nothing but set of equality constraints representing power flow equation. Then small f is nothing but objective function, that we all know. Okay, so L of x comma u comma p is equal to f of x comma u plus lambda dash into g of x comma u comma p. So this is the Lagrange's function. So next, Lagrange's function is rewritten as, like, we need to substitute what is objective function, that already we derived. Already we have derived here. So f of x comma u, you have to substitute. Okay, so while substituting, by like f of I into pi for all generation plus f of reference into p of reference into e comma theta plus here lambda dash. So lambda dash is nothing but lambda 1 comma lambda 2 up to lambda m. So this g of x comma u comma p is nothing but, this already we derived, that is p of e comma theta minus pi net, qi of e comma theta minus qi net, pk of e comma theta minus pk net, from this equation, from the previous equation. Yeah, from the previous equation, g of x comma y. So just like that substitution, that's it. Just like that substitution. So after substituting, now we have Lagrange's function, that is the single objective function, and m Lagrange multiplier, one of each of m power flow equation. Okay, to minimize the cost function subject to constraint, we set the gradient of Lagrange's function to 0. Next step, you know, after training the Lagrange's function, similar, whatever you know, the same step, we have to differentiate and equate it to 0. So like dou L is equal to 0, differentiation with respect to L and equate it to 0. So to do this work, we have to break up the gradient vector into 3 parts corresponding to the variable x comma u comma lambda. Okay, so del of L x is equal to dou L divided by dou x, that is nothing but dou f divided by dou x plus dou g divided by dou x, the whole transport of lambda. Then dou L of u is equal to dou L divided by dou u, that is nothing but dou f of dou u plus dou g divided by dou u, the whole transport of lambda. Again, del L of lambda is equal to dou L divided by dou lambda, that is nothing but g of x comma u comma p. Okay, so here we have to calculate the dou f by dou x. Dou f divided by dou x is nothing but, that is a vector. Okay, that is the vector we already framed, that is nothing but dou divided by dou p reference, f of reference of p reference into dou p reference divided by theta 1. So next is dou divided by dou p reference, f of dou p reference into dou p reference divided by dou e1. This will continues for n generating units, whatever you consider. Okay, so this is nothing but dou f divided by dou x. So just like that, we are differentiating with respect to, okay, x. Okay, so already f is there, so just like that we are differentiating this. Next, dou g divided by dou x. Dou g divided by dou x, actually this is Jacobian matrix. Jacobian matrix. If you see like this dou g divided by dou x, dou p divided by dou theta 1 into like next dou p divided by dou e1, dou p divided by dou theta 2, dou p divided by dou e2, like that it may continue. So same like that q1, dou q, this is p, next is q, dou q1 divided by dou theta 1, dou q1 divided by dou e1, dou q1 divided by dou theta 2, dou q1 divided by dou e2, like that it may continue. Next, dou p2 divided by dou theta 1, dou p2 divided by dou e1. Next, similarly dou p2 divided by dou theta 2, dou p2 divided by dou e2, like that it may continue. Similarly q2 also, dou q2 divided by dou theta 1, dou q2 divided by dou e1, then dou q1 divided by dou theta 2, dou q2 divided by dou e2, like that it may continue. Note that this matrix must be transposed, okay, for using that. Why? Because here we have utilized, we derived like transpose here, dou g divided by dou x of transpose. So again we need to transpose this matrix. Okay, so if you calculate dou f divided by dou u, it will come like dou p divided by dou p1 divided by dou f of f1 of p1, dou p2 divided into f2 of p2, like that it may come. In another terms, dou g divided by dou u actually consists of matrix of all zeros with some minus 1 terms on the diagonals, which corresponding to the equations in g of x of u comma p. Okay, so the solution of gradient method of optimal power flow is as follows. First one, given a set of parameter p, assume a sorting set of control variables u, then solve the power flow problem. Okay, then again solve for lambda. So lambda is equal to minus of dou g divided by dou x, the whole transpose, the whole inverse into dou f divided by dou x. Now substitute lambda into that gradient of L. This we already derived, no? Gradient of L, that is dou gradient of L is equal to one big formula. Yeah. Gradient of L. Yeah. Gradient of L. So that's why we divided this into 3. So like that we need to solve this problem. Okay, gradient of L. Okay, like that we need to solve this problem and we need to complete the solution. So, okay, so first objective function we need to frame. So instead of objective function is very complex, we have taken as 3 variables, x comma u comma p, that we have taken. So again we are, after framing the Lagrange's function, it is very difficult to solve. So we have divided into 3, so that we can easily solve the problem. So that we divided and we try to solve that